Good morning, everyone. Yeah, this week is our last week. Happy, excited? Yeah, hope you really learned something from uh this course. Yeah, we talk about from the simple harmonics motion to the traveling waves and to the like sound wave, string wave, and then to the light wave. Yeah, and then we talk about for the light, it can be act like a wave, like a so we have we learn some like wave optics. Also, like the light have the it's just a particles, and it's just similar like a rain. Yeah, so we just also learn the rain like optics, and after that we learn the electric things and the electrostatics, and for the like still like electric, yeah, electric things. For example, the atoms, the charges, and the like and all the electric fields, and the electric and potential, and electric potential energy. Yeah, all these electric statics. And also after that, we learn some like electric dynamics, like a current. Yeah, because this is a motion of charge. And for the current, we learn some more Ohm's law, and then resistors and capacitors, how those things like a like a form a circuit, and how to analyze this circuit, all these things step by step. Yeah, actually, yeah, this week we will focus on the magnetic things. Yeah, magnetic fields and forces and other like magnetic things. And next week, no, not no, there's no next week. So sorry. Don't be worried about that. Yeah, like next chapter, yeah, we will like learn some like electric and magnetic things combination, like electromagnetic things. Yeah, so this is what we focus on for the magnetic things this week. And yeah, time is flying. So yeah, this is our just last week. And if you can review like yeah, I know I haven't graded all the labs for now, and I just want to give you the more time for that. If you can finish all of labs before this Sunday, and yeah, and I will accept that. But there is some like a penalty. But if you can give me the reasonable like excuse, like a uh, yeah, I will give you the full credit. And also, if you like have some question about the homework, the exams, or like homework questions, exam questions, or like the homework, or like exam grading, and you also can email me, or like text me. Yeah. Okay. Let's begin today's class. And let me share my screen. Yeah, like I said, uh, this week we will focus on magnetic things, and for the chapter like 24, yeah, we focus on magnetic fields and forces. Sorry. And for the 20 like chapter 25, we focus on the electric and magnetic combination. And we call it like a electromagnetic things. Yeah, and you will know that. And so in this week, in this chapter, we focus on magnetic fields and forces. Okay, let's start. And yeah, for the chapter 24, this chapter's goal is to learn about magnetic fields and how magnetic fields exert forces on currents and moving charges. Yeah, you can see uh, like yeah, we have already learned the electric fields. Yeah, so actually it's similar, but have some difference, and you will know that. And how the magnetic fields exert forces, and we know like the electric fields also exert the ex sorry. Yeah, like the electric fields also like exert like electric forces. If you remember what we talked about in NASA chapter. Yeah, I think not just NASA chapter, the chapter before NASA chapter. Yeah, it's chapter from chapter 20 to chapter 23. Yeah, we talk about electric fields and electric forces. Yeah, actually, the magnetic fields and magnetic forces is very it's similar. Yeah, we will talk about that. Yeah, and also you can see on currents and moving charges. Yeah, we know like the currents and moving charges is are related to electric things. Am I right? Yeah, we talk about this. Yeah, so which means the magnetic things are very like has a relationship with electric things. Yeah, we will talk about that. Okay, and this is today's goal. First, we will explore magnetism, and then we will learn what is like a magnetic field. And after that, we try to understand electric currents also created magnetic fields. Yeah, you will know that. Yeah, actually, electric currents can also create magnetic fields. Study how to finally we will talk about how to calculate the magnetic field due to a current. Yeah, because the electric current can create it, and how then we will know and then we'll figure out how to use a current to calculate magnetic field. Okay, this is what we talk about. We will talk about in today's class. Let's begin. Yeah, before we start this chapter, let's preview what we will learn in this chapter. First, we will talk about magnetic fields. Yeah, compass. I think everybody knows these things. Am I right? Yeah, a compass is a small magnet that will rotate to line up with a magnetic field. Yeah, so yeah, we will learn like how to use compasses and other tools to map magnetic fields. And then we will talk about sources of the field. Yeah, magnets produce a magnetic field. You can see if you, I think you guys must do some labs about these things in at high school. I think yeah, so so do current carrying wires, loops, and cores, and you will know like the current can generate, can create magnetic fields. You will learn how to describe the magnetic fields created by currents, and these arrow fillings show the magnetic field shape for this current carrying wire loop. Yeah, we will learn these things. Okay, and finally, we will talk about the effects of the field. Yeah, magnetic fields exert forces on moving charged particles and electric currents. Yeah, we will see how the motion of charged particles in the Earth magnetic field gives rise to the aurora. Yeah, you can see this aurora. I think everybody knows that, but maybe not everybody see that. Yeah, but you know, like the motion of charged particles in the Earth's magnetic field gives rise to this aurora. Yeah, yeah, we will talk about this. Yeah, in this chapter. Okay, before we talk about this chapter, let's look back something. And electric fields, yeah, we talk about a lot in since chapter 20. Yeah, in chapter 20, we described the electric interaction between charged objects in terms of the field model. Yeah, we talk about a lot those things like how like charged objects like have the in electric interactions. Yeah, and we learned how to draw and interpret the electric field of dipole. Yeah. Do you remember what is dipole? Yeah, you can see like there is a charge, a positive like a charge. There is a negative charge, and those positive and negative should be equal. Like the magnetic like it should be equal, but the sign is positive, is opposite. Yeah, and then we call it a dipole. In this chapter, you will see how a magnetic dipole creates a magnetic field with a simple structure. Yeah, like we have already learned electric dipole. In this chapter, we will talk about the magnetic dipole. Yeah, created a magnetic field. And okay, let's continue. Yeah, before we talk about this chapter, and let's think this question. An electric dipole in a uniform electric field experiences no net force, but it does experience net torque, and the rotation of this dipole will be like we know like this is the electric field. It should be from the positive to negative. So which means this should be the positive like one charges source, and this is negative charges source, which means this one should go this direction and this one should go this direction. Am I right? So which means it should be what? Counterclockwise. Does it make sense to you? Yeah. So the answer should be this one. Yeah. So try to review what we have already talked about. Okay, let's talk about today's things. And firstly, let's talk about magnetism. Yeah, and we begin our like investigation of magnetism by looking at the results of some simple experiments, and we will investigate how magnets interact with compasses and other magnets and various types of materials. Yeah, let's review some experiments. Okay, and the experiment one, you can see if a bar, yeah, this is a bar magnet, is taped to a piston of cork and allowed to float in a dish of water. Yeah, this is a bar magnet, and this is a cork, and this is water, and this cork is like floating on the water, and this bar magnet is put on the cork. Yeah, it turns to align itself in an approximate north-south direction. Yeah, it will. This one will like the direction and will like point north-south direction. The end of a magnet that points north, we call it the north pole, and the other end is the south pole. Yeah, that makes sense to you? Yeah, it's just like we define what is north pole, what is south pole. If a bar magnet, and if after it is still, and you see the part point to the north, and we call it north pole, and the part like a point to south, we call it south pole. Yeah, like this one, this is the north pole, this is south pole. And also a compass, actually it's just similar with is a bar like a magnet, but a different shape. Yeah, a magnet is free to pivot like this is called a compass. Yeah, if a compass will pivot to line up with a nearby magnet. Yeah, you can see if there is a nearby magnet, and then the source will point direct to north. And yeah, if you like opposite, just flip this bar magnet, and then the north will point to this bar magnet. Does it make sense to you? Okay, let's continue. This is experiment 1. And then the experiment 2. Yeah, and if the north pole of one magnet is brought near the north pole of another magnet, yeah, similar like this, and they repel each other. Yeah, two south poles also repel each other. If you flip this one and flip this one, and you here if it is and it will also repel each other. And the two south poles, yeah, but the north pole of one magnet exerts an attractive force on the south pole of another magnet. Yeah, if you put a bar magnet like this, and the other like this is S, this is N, and this is S, and you will find that there is a attractive force. Yeah, this is experiment 2. And let's review experiment 3. Yeah, cutting a bar magnet in half produces two weaker but still complete magnets, each with a north pole and a south pole. Yeah, you can see here. If we just there is a bar magnet, this is the N pole, north pole, and this is the south pole. And if you cut it cut it in half and like produces two, and those two actually is weaker. The magnetic field and forces is weaker than the original one, but still like two still complete magnets. Yeah, one just has a south pole and a north pole, and the other also has a south pole, north pole. But you can see, if you observe very carefully, you will see like the north is just if you cut from this line, and then this part will become those one, and north is here and south is here, and then south is here, north is here. Yeah, that makes sense to you. Okay, this is experiment 3. And experiment 4, like magnets can pick up some objects. Yeah, if I think you must have this like labs in at high school. Yeah, and magnets can pick up some objects such as paper clips. Yeah, but not all. If an object is attracted to one pole of a magnet, it also attracted to the other pole. Yeah, you can see if you use the north pole to can attract those clips, and also you can use south pole to connect attract this thing. But not all things can be like attracted. Yeah, for example, this I think this might be a core. Yeah, this core cannot be. Yeah, yeah, most materials. Yeah, like including copper, aluminum, and glass and plastic. Experiments no force from a magnet. Yeah, and most materials cannot be like attracted by the magnets. Yeah, that makes sense to you. Okay, this is experiment 4. And this is experiment 5. When a magnet is brought near an electroscope, yeah, the leaves of the electroscope remain undeflected. If a charged rod is brought near a magnet, there is a small polarization force like the ones we studied in chapter 21, as there would be on any metal bar, but there is no other effect. Yeah, if there is a electroscope here. Okay, yeah, we talk about 5 experiments, and what do these experiments tell us? Yeah, like you can see from those experiments, yeah, magnetism is not the same as electricity. Yeah, you can see if you use like an electroscope, like near a magnetic is brought near a electric scope, the leaves of the electric scope remains undeflected. Yeah, it's not like the electricity. Yeah, but the magnetic poles and electric charges share some similar behavior, but they are not the same. Yeah, this is what we can get from those 5 experiments. Yeah, yeah, magnetic poles. You can see it's very similar with the electric poles. There is a negative, there is a there is positive, negative. Yeah, it's very similar with the electric poles, but yeah, they share some like similar behavior, but they are not the same. Yeah, we will talk about how they are similar, how they are different. Yeah, okay, let's continue. Yeah, yeah, magnetism is a long-range force. Actually, yeah, the electric is also a long-range force. Yeah, magnets do not need to touch each other to exert a force on each other, just like 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 the charge, am I right? Yeah, the charges do not need to touch with each other to exert a force on each other. Yeah, it's the magnets is a similar it's similar. Yeah, magnets do not need to touch each other to exert a force on each other. Yeah, like you can see the like poles. Yeah, two north will like repel each other, and one north, one south will like attract each other. Yeah, and magnets have two types of poles called north and south poles. Yeah, we talked about that just now. And thus are magnetic dipoles. Yeah, this is magnetic dipoles. We call one is north poles and the other is south poles. And for the electric dipole, one is the like a negative dipole, the other is a positive dipole. Yeah, that makes sense to you. Yeah, cutting a magnet in half yields two weaker but still complete magnets, each with a north pole and a south pole. Yeah, but for the electric things, there is no this feature. Yeah, the basic unit of magnetism is thus a magnetic dipole. Yeah, the basic unit of magnetism is thus a magnetic dipole. Okay, dipole, sorry. And the poles of a bar magnet can be identified by using it as a compass. And other compass, sorry, let me check. Yeah. The poles of a bar magnet can be identified by using it as a compass. And other magnets can be identified by testing them against a bar magnet. Yeah, a pole that repels a known south pole and attracts a known north pole must be a south magnetic pole. Yeah, doesn't make sense to you. Yeah, because this one like a repel source, which means it has a same like a pole, same, yeah, it is source magnetic pole, and for the because it is source magnetic pole, it must attract north pole. Yeah, you can see the needle of a compass is a small magnet. Yeah, okay. Only certain materials called magnetic materials are attracted to a magnet. Yeah, you can see here, we talk about in experiment 305, 304. Yeah, the lesson it is 4, yeah. Yeah, it is, yeah, it is in the experiment 4. Yeah, like yeah, only certain materials called magnetic materials are attracted to a magnet. Yeah, and this the most common magnetic material is iron. Yeah, I think everybody knows that. Am I right? Yeah, the magnetic materials are attracted to both poles of a magnet. Actually, you can see it's the iron. Yeah, they don't have the magnetic feature. They are not magnetic. They're not like they don't have the magnetism. Yeah, they just like but this material can be attracted by magnetic can be attracted by a magnet. And yeah, since these materials don't have like magnetism, so it can be attracted by it's similar like a neutral. Yeah, so it can be attracted to both poles of a magnet. It can be attracted to the source also north. Yeah. It kind of neutral, yeah, but not all the materials can be attracted by a magnet. Yeah. And let's review this question. If a bar magnet is flipped over and the south pole is brought near the hanging ball, and the bar will be, because this is steel, so it contains the iron. So we know the irons can be attracted by either of these poles. So it will also be attracted to the magnet. That makes sense to you? Yeah, so the answer should be A. Yeah, and let's talk about this one. If a bar magnet is cut in half, you end up with, yeah, we talked about this a lot just now. And because if you cut it from here, which means this one become a new and a weaker one, and this one will become a new and a weaker one, and this one become like S, this one S, like that. Yeah, so which means it should be as yeah, this one. Does it make sense to you? Yeah, yeah, it is C. Okay. Yeah, we have already talked about what is magnetism. Yeah, it's similar with the electric, but also have differences. Yeah, let's continue to talk about the magnetic field. Yeah, and you can also watch this video for magnetic fields. And I will now play the video. Okay. And what is the magnetic field? Yeah, every magnet sets up a magnetic field in the space around it. And if another magnet, such as a compass needle, is then brought into this field, the second magnet will feel the effects of the field of the first magnet. Actually, it's similar like a electric field. Yeah, but yeah, we will talk about. And you can see, let's review the electric field. Yeah, an electric dipole, yeah, we know like the electric dipole is there is a positive, there is a negative, and it's the same. And experiments torque when placed in an electric field. This is the electric field. Yeah. Yeah, and the torque caused by an electric field tends to align the axis of the dipole with the field. So the direction of the electric field is the same as the direction of the dipole's axis. Yeah, the torque on dipole is greater when the electric field is stronger. Hence, the magnitude or strength of the field is proportional to the torque on the dipole. Yeah, we talk about in electric field. Yeah, we just review this, and actually the magnitude or strength of the field actually is similar with we talk about in the electric field. And you can see this is a magnetic field. Yeah, for the magnetic field, it usually like for example, the direction is just like this, and this is a compass, a magnetic dipole. Yeah, this is S, and sorry, a magnetic dipole. Yeah, rotates so that its north pole points in the direction of the magnetic. Yeah, you can see this is the original one, and the like the compass will like rotate so that its north pole points in the direction of the magnetic field. Yeah, a magnetic field exerts a torque on the compass needle, causing the needle to point in the field direction. Yeah, it's similar with the electric field. Okay, and because the magnetic field has both a direction and a magnitude, we represent it using a vector. Yeah, B, like there is a arrow. Yeah, we use this to represent the magnetic field. Do you remember what we use to present the electric field? Yeah, we use the E. Am I right? So here we use B. Okay, B represents, yeah, if you didn't put the arrow here, which means it just represents the magnitude or strength of the field. It's just like a magnitude, yeah. The direction of the magnetic field is the direction that the north pole of a compass needle points. Yeah. The strength of a magnetic field is proportional to the torque felt by a compass needle as it turns to line up with the field direction. Yeah, this is the relationship between the strength of the magnetic field and the torque. Yeah. Yeah, doesn't make sense to you. Actually, it's similar to the electric field and the electric torque. Yeah. Okay, let's continue. You can see this is a bar magnet, and this is a compass, and this is ice. The compass like points to the right beginning of the compass like points to the right upper right, so that is the direction of like a this is the direction of like of the magnetic field. Yeah, and here this compass points to the lower right, so this direction is this point is the direction of the magnetic field. Yeah, and you can see this is the direction of the field, the magnitude of the field. Like here, because this one like is further from this bar magnet, so here has a weak field. Like the needle turns slowly. If you do this experiment, you will like know that. And here is near to this like a bar magnet, so the needle turns rapidly because the strong field. That makes sense to you? Yeah. Okay. So, yeah, and we can produce a picture of the magnetic field by using arrow filaments, very small, elongated grains of arrow. Yeah, I think you must like have already done these similar experiments, yeah, at high school or earlier. Yeah, you can see like each arrow filling acts like a tiny compass needle and rotates to point in the direction of the magnetic field. You can see here this is the black one, the small black one. It is each iron filling acts like a tiny compass needle and rotates to point in the direction of the magnetic field. You can see it will, if you observe, like that's, yeah. If you observe it very carefully, and you will know that, yeah, the black one, it is like a point in the direction of the magnetic field. And since the, yeah, this is like where the field is strong, and the torque easily line up the feeling. Yeah, you can see here because it's very near to the source magnet. Yeah, this bar magnet. So here, yeah, here is strong. Yeah, it's very strong. Here the field is very strong, so the torque easily line up the fieldings. Does it make sense to you? Yeah. Since the poles of the arrow fillings are not labeled, a compass can be used to check the direction of the field. Yeah, so you can put some small compass here. Sorry. Yeah, you can put some campuses here, and you can see you put it here, here, and you can see if this is north point. Yeah, this here. In this point, the direction is here, and in this point, the direction is here, and in this point, the direction is here, and in this point, the direction is here. Yeah, that makes sense to you. Yeah. So like Yeah, you can see here is the field is weak, so the torque barely line up the field. Yeah, the feelings. Yeah, that makes sense to you because it's far from this bar magnet. Okay, you can see the magnetic field of the magnet points away from the North Pole and towards the South Pole. Yeah, if you observe carefully, you can see the magnetic field of the magnet points away from the North Pole. Yeah, you can see the direction here, direction here. Yeah, which means it will point out. Yeah, point out. Yeah, and then it will like toward to South Point. Yeah, you can see the direction here. If you put the compass here, put the compass here. Yeah, you can see it will point towards the South Pole. Yeah, since the poles of the arrow fields are not labeled, a compass can be used to check the direction of the field. Yeah, we have already talked about that. And and then where the field is strong, the torque easily lines up the feelings. Yeah, this is by from the experiment. Where the field is weak, the torque barely lines up the feelings. Yeah, and yeah, we have already talked about this. And the magnetic field vector representation is useful if we want to represent the magnetic field at one particular point. Yeah, if we want to overall representation of the field, magnetic field lengths are often simpler to use. Yeah, we will talk about what is magnetic field vectors and what is the field length. Actually, the magnetic a magnetic field vector. Yeah, we can use it to represent the magnetic field at one particular point, and we can use magnetic field length to represent the overall field. Yeah, okay, let's continue. Yeah, mapping out the field of a bar magnet using compasses. If you put many small compasses around this bar magnet, you will find the magnetic field vector and magnetic length. Yeah, you can feel the length. Yeah, you can see the magnetic field vectors point in the direction of the compass needle. Yeah, this one. Yeah, this is the n. Yeah, we talk about it. And the direction is the n north pole points. Yeah, this is the direction. This is the magnetic field direction. Yeah, doesn't make sense to you. Yeah, we represent the stronger magnetic field near the magnet by longer vectors. Yeah, doesn't make sense to you because here, this one is nearby this one, so we use the longer vector. And if like here is because it is weaker than this one, so we use a shorter vector. Yeah, that makes sense to you. Okay, and then before we talk about more about magnetic field vectors and the field length, let's talk about some questions. Yeah, a compass is placed at the black dot. Yeah, in which direction will the compass point? Yeah, we know the compass will the direction the electric field is away from north, pointed to south. Yeah, so which means in here it direction should be this way. Am I right? So and we know the for the compass it should be the north pole point. Yes. So which means it should be this one. That makes sense to you? Yeah, the north pole point. Yeah. So the answer should be B. That makes sense to you? Okay, let's check this one. A compass is placed as a black dot. In which direction will the compass point? Yeah, we know actually we can check here. Here, yeah, it's just similar with this point and this point because the electric field should from north to south, from north to south. So for this point, it is for the compass, it should point this direction. Am I right? So obvious, the answer for this one should the north should the north pole should point to this one. Am I right? So the answer should be A. Does it make sense to you? Yeah. Okay, let's find this one. A compass is placed as the black dot. In what direction will the compass point? Yeah, this one is also we check this one. Yeah, and here for you can see here is in the middle of this bar. So which means one is just point to S. The other is just like a point away. Am I right? So which means from here, for example, this point should the compass is here. It should point to from the if this one, because this one also like from this thing to this way thing, and it will for this it is pointed to upward, and for here it is should left. Yeah, it should be left. It should also point this direction. Am I right? But if that makes sense to you, so which means it should be D. Am I right? So the north should be pointed to the like a source. Yeah. So which means the answer is D. Does it make sense to you? Yeah. Okay. Let's check this one. A compass is placed at the black dot. In which direction will the compass? Yeah. For this one, and it should be N pointed S, and it in the middle, so it should be point this direction. And for this one, N to the S, it should be this one. So which means this two, because those two are same, those two bar magnetic are same. So which means the magnetic field will be cancelled in this point. Yeah, that makes sense to you. Yeah, so the answer should be E. Yeah, because those dots will be affected by two bar magnets. Does it make sense to you? Okay, let's check the next things. Yeah, let's continue to talk about magnetic field vectors and field lengths. After we talk about what we talk about and those quick check questions, yeah, you can see we can draw the magnetic field length of a bar magnet. Yeah, you can see here is N like north pole, and this is the south pole, and the magnetic field should leaves its north pole and enters its south pole. That makes sense to you? Yeah, we have already talked about it. And the every magnetic field length leaves the magnet at its north pole and enters the magnetic at its south pole. And also the direction of the magnetic field. This we call this at any point on the field line is tangent to the it is tangent to the line. Yeah, this is the line and the tangent. It's similar like the magnetic field. Does it make sense to you? Yeah. It's similar to the electric field. Yeah, it actually electric field vector. Yeah, and the lines are joined closer together where the magnitude beam of the magnetic field is greater. You can see here it is closer, so which means the magnetic field is greater here, but it's weaker here. Yeah, and here is also like because it's closer, so it is greater. That makes sense to you? Okay, let's talk about a single bar magnet. Actually, we have already talked about the single bar magnet. The magnetic field length start on the north pole, yeah, the right one, and end up the south pole and the one one. As you move away from the magnet, the field lengths are further apart, indicating a weaker field. You can see here. Let me give you you can see here, because it is away from the magnet. So there is a weaker field. Yeah, here is a weaker field. But here it is close to the magnet. So there is a great stronger field. That makes sense to you. Okay, you can see close to the magnet, we can more clearly see how the field lines uh, always start on north poles and end on south poles. Here you can see if we zoom in, yeah, this like a image, and you can see we can more clearly see how the field lines away start. Yeah, start from the north. This is north, this is south. Yeah, and goes to the source. Yeah, does make sense to you? Yeah, and then we can use electric field length. Yeah, to represent this. This is the, we call it electric field length. Yeah, from the north to south, from the north to south, and closer, and it is stronger, and further it will weaker. Does make sense to you? Okay, this is for the a single like a bar magnet, and let's talk about two bar magnets. Yeah, and also unlike poles facing, like this is and this is north and this is south. And with more than one magnet, the field lines still start on a north pole and end on a south pole, but they can start on the north pole of one magnet and end up on the south pole of another. You can see here. Let's draw the magnetic field lines. Yeah, you can see this can goes to this direction. Yeah, from north to south. Also, it can goes directly to the other the south pole of the other one. That makes sense to you? Yeah. Okay. And let's talk about the two bar magnets, but like poles facing, which means this one is north, no, also north. And with two like poles placed nearby, the field lines starting on the north poles curve sharply towards their south poles in order to avoid the north pole of the other magnet. You can see here it is it will like because it will not go into the north pole, so it will like curve sharply, yeah, toward to their south pole in order to avoid the north pole of the other magnet. That makes sense to you? Yeah, because it's like poles. Yeah, and magnets can have more than one pair of north-south poles, and the poles do not need to be at the end of the magnet. Yeah, you can see here. It has yeah, it have more than one pair. Yeah, it can have more. Yeah, and the poles do not need to be at the end of the magnets. Yeah, here also can have the magnet. Yeah, and for example, the magnetic field of a refrigerator magnet. Yeah, actually this one is a like a refrigerator magnet. You can see the magnetic field extends mostly out of this side of the magnet, and the poles of the magnet are arranged like long U-shaped magnets. Yeah, you can see here. This is the north pole, this is south pole, and this is south pole, this is north pole. Yeah, it's just like arranged like a long U-shaped magnet. And also, yeah, that makes sense to you. Yeah. Okay, the pore structure of a refrigerator magnet can be revealed by a special film that contains fine iron fillings. You can see this is a this green one is a magnetic like a refrigerator magnet, and this green one is a special film. Yeah, and the pole structure can be revealed by a special film that contains fine iron fillings. Yeah, yeah, this is a experiment. Yeah, and you will know like the for a magnetic for a refrigerator magnet, and the small like magnet will arrange by this by this shape, yeah, U shape. That makes sense to you? Okay. And yeah, you can try this by yourself. You can use two identical flexible refrigerator magnets. Yeah, remember, it should be two identical. Yeah, and for nice demonstration of their alternating pole structure, place the two magnets together back to back, then quickly pull up across each other, noting the alternating attraction and repulsion from the alternating poles. If you pull them quickly enough, you will hear a buzz as the magnets are rapidly pushes apart and then put together. Yeah, because it has the magnetic field forces. Yeah, then yeah, you can try this by yourself. Okay, let us talk about the other one. Okay, let's talk about the magnetic field of the Earth. Yeah, I think everybody know like our Earth has is a big magnet. Yeah, the South Pole. Yeah, this is the South Pole, and this is the North Pole. The South Pole of the Earth's magnet is located near, but not exactly coincident with the North geographic pole of the Earth. Yeah, you can see the North Pole of the Earth's magnet is actually in southern Canada, not right at the North geometric uh, pole. Yeah, here. This is the source, uh, like a source pole. Yeah, actually, the source pole of the Earth magnet is not exactly in the in this point. It's just like a in the northern Canada. Yeah, this is just a you need to know. And here, this line is the Earth's rotational like axis, and this one is the North geographic pole, and this is the equator, and this one is the North magnetic pole. Yeah, and this is the South magnetic pole. Yeah. Okay, so this is why the North Pole of a campus points uh, geographically north. Yeah, that makes sense to you? Yeah, because let me add more details. Because this is here is the south magnetic pole, and if you use a compass, which means the north pole of compass will point to this direction, because this is the south magnetic pole. Yeah, and so we define this is north geographic pole because when the compass pointed to north, we know it's a north direction. So we just define this here is north geographic pole, and we didn't define this like south geometric geographic pole because yeah, you can see this is north. Obvious, this is south geographic pole. Am I right? You know, like the campus in Chinese name is we call it point north needle. Yeah, because it always points north. Yeah, does this make sense? Make sense to you? Okay, let's continue. And the Earth's magnetic field has components both parallel to the ground, like horizontal, and perpendicular to the ground, vertical. You can see here, here is this point near the poles, and the field is tipped at a large angle with respect to the Earth's surface. And yeah, because near the pole, and this is N, and this is S. So, which means the N, the compass N will point to the like a north geographic pole, yeah, will point to this one. And here, yeah, here, because this near the equator, yeah, the field is nearly parallel to the Earth's surface. Yeah, this, and which means this angle will become smaller, yeah, because it will point to, yeah, this direction is like a north geographic pole, yeah, north geographic pole. So which means this one will point this direction, and this one will point this direction. Does it make sense to you? Yeah, ordinary north pointing compass responds only to the horizontal component of the field, but a compass free to pivot vertically will tilt downward as well. Yeah, the deep angle is the angle from the horizontal. That makes sense to you, because you can see this is the like this is the angle, and this is the angle. Yeah, you always can. It's just from this tangent line. Yeah, because this is electric magnetic field. Yeah, and this is just like a tangent. This tangent geometrical, and this is just the angle is just this line, and between this, yeah, that makes sense to you. This we call it the deep angle. It's angle from the horizontal. Okay, and let's continue. And magnetostatic bacteria have strongly magnetized base of iron in their bodies. Yeah, actually, this is a bacteria. Yeah, it those kind of bacteria have strongly magnetized base of iron in their body. You can see here. Their bodies rotate to line up parallel to the Earth field, just like a compass. So this like a bacteria prefers a low oxygen zone near the bottom of bodies of water. If the water is disturbed and they are displaced upwards, they follow their vertical component of the Earth field downward. Yeah, because this kind of bacteria have the iron in their bodies. So which means like these bacteria prefer the low oxygen zone near the bottom of the body of water. Yeah, because the water, if the water is disturbed and they are displaced upwards, they follow the vertical component of the Earth field downward. Yeah, so this is the application of magnetic field of the Earth. Okay, let's continue. Yeah, let's review a conceptual example. Yeah, homing pigeon navigation. Yeah, this is about biology example. Yeah, this is there is evidence that the pigeons use the Earth's magnetic field to navigate. Although the exact mechanism is not understood, researchers suspect that magnetic sensors in the bird's head are responsible for detecting the Earth's field. To investigate this question, researchers attach small magnets to the back of the pigeons and measure their ability to find their way home. Yeah, actually, you can see for the pigeons and many other like birds, they can always find like some birds, they fly to south in winter and fly back to north in spring. Do you know like that kind of bird? Yeah, they have this ability, can navigate, use Earth's magnetic field. Yeah, and you can see to investigate this question, researchers attach small magnets to the backs of pigeons and measure their ability to find their way home. Okay, let's see how can they do it. Yeah, the figure shows a pigeon with a magnet on its back here and fly north from its release point in New York State. In order to make the bird think that it's flying south, should the like a pole P of the magnet be a north or a south pole? I think this one is not difficult, am I right? And you can see the figure 24 .78 shows that the Earth field at northern latitudes points to the north and down. Here, this is the south, this is the north, and the figures shows the Earth field. This is the Earth field. Point to this direction. Yeah, which means like this is like Earth north, and this is Earth south. And yeah, for the pigeon to think it's flying south. Yeah, sorry, I just like some format issue. I just adjust it. Yeah, for the pigeon to think it's flying south, the magnetic field at its head would need to be flipped north to south. That makes sense to you, as shown by vector. Yeah, B south. And the magnet should thus create a field that adds to B earth to give B south, as the upper figure show. This figure. Actually, it's just yeah, this figure. Yeah, and this field is directed to the south, or in lower figure to the left into the magnet. This shows that the pole P is a south pole. Yeah, this one, because you can see it should point. Let the pigeon know. It's flying to the south north. Yeah, so which means this one should be the source, and then it will like give this pigeon like, oh, I'm attracted by the north. I'm point to the north. Does it make sense to you? Yeah. Okay. When the pigeon is flying north, it is flying towards the south pole of the Earth's magnet. Yeah, we talked about it. Makes makes sense. Then that a stronger south pole behind it would turn its magnetic orientation around. Does it make sense to you? Yeah. Actually, you can see here, like either if there is no like this bar magnetic and the like this, yeah, because this is like a Earth source. This is Earth. Okay, let us use this picture. I think this one will be easier to talk about that. Yeah, you can see here. This is the Earth magnetic. Actually, this is the south magnetic pole, and this is north magnetic pole. But like we talk about, this is the north direction. This is a north like a geographic pole. Yeah, so this is north like a direction. This is the south direction. And if a pigeon, like usually in the real world, it will fly to south. Am I right? From like for them here to fly to here. So which means it should like opposite this one. But now we want to put a extra bar magnetic to let him to like observe let this bird think, let this pigeon think, oh, this direction is like a source. So which means we just put a north pole, no like that P, yeah, this P, yeah, this P. yeah, should like point to if this is if in this bird's head, yeah, he had the magnet in its body, and this magnetic it must like a direction to the source, yeah, direction to this one, to this is source. Sorry, right? Sorry. Yeah, this is source. This part is source. So which means he in his head it must has like a source pole, but we want to like flip it. So which means we want to put an extra like magnetic let this bird think this direction is the source. So which means yeah, because this is the source magnetic pole. So which means we should put a magnetic, this is we should put a magnetic and this is north pole, and then like have a attractive like a force, and let this bird fly to the source. That makes sense to you. So that's the reason why we put the we like the like pole P is a south pole. Does it make sense to you? Yeah, like yeah, this one is just a simple like this drawing. Yeah, because for the Earth, this is Earth like electric magnetic field, and this is actually magnetic field, which means and from north to south, from north pole to south pole. Yeah, north to south pole. Yeah, this is just a direction, south direction and north direction. Yeah, we want this one to fly this pigeon to fly to this direction north. Yeah, so which means we need to put because this is south pole for the like Earth magnetic, yes, magnet net. Yeah, so we need to put a north here. That makes sense to you? Yeah. Any question? Just let me know. Okay. Yeah, we have already talked about this. When the pigeon is flying north, it's flying towards the south pole of the Earth's magnet. Yeah, but just pay attention. Like the south pole of the Earth's magnet is just the north direction in the like geographical like direction. Yeah, don't mess those two up. Yeah, it makes sense. Then that a stronger south pole behind it would turn its magnetic orientation around. Okay, let's continue to talk about electric currents. Also, like create magnetic fields. Okay, you also can like review play some video for the magnetic field sources. Yeah, and I will now play the video here. Okay. Yeah, like a campus will react to the presence of a bar magnet. Yeah, we talked about this just now. And a campus will also deflect if you place the campus near a well and pass a current through the well. When the current stops, the campus goes back to its original like orientation. Actually, this is a lab you can do. Yeah, experiment. This is a fact like that. Yeah, this means that an electric current produces a magnetic field. The shape of the field lines depends on the shape of the current carrying well. Yeah, well. Okay, yeah, this these things tell us like electric current also create magnetic fields. I don't know if you do these similar experiments before. Yeah, like if you create like a circuit, there is a current in through a wire, and if you put a campus near the wire, and the campus will like um, go like the campus will like mm, pass if you pass yeah a campus will deflect. Yeah, yeah, you can do the similar experiment, yeah, if you like. Okay, and let's talk about if a current in a long straight wire. Yeah, and the magnetic field lengths from circles around the wire. The iron fillings are less affected by the field as the distance from the wire increases. Yeah, indicating that the field is getting weaker as the distance from the wire increases. Yeah, like here, if there is a current inside the wire, no matter the direction, and there will have a, because this wire is a straight wire, and there will be like a magnetic field, and you can see for there is some like iron fillings, and near the wire, and there will be a stronger electric magnetic field, and if there is a distance become longer, and the field is getting weaker. Yeah, that's yeah. This is there's a simple drawing. Does it make sense to you? Yeah, this is just like we observe from the experiment. And okay, if there is like a circular loop, yeah, if there is a loop thing, yeah. For example, there is a ring, there is a circular. Yeah, the magnetic field length curves through the center of the loop. You can see there is curve, the magnetic field length curves through the center of the loop, around the outside and back through the loop center. You can see back, yeah, from back, yeah. Just like this. This is a simple like drawing. From forming complete closed curves. The field lengths far from the loop look like the field lengths far from a bar magnet. Yeah, you can see this one actually. If you let us to see the magnet. Sorry, I think it is this one. Yeah, you can see if you compare this one with sorry, with yeah, with this one, and you will find it's similar, like yeah, it's just like from the yeah, far, like the field length far from a bar, like a magnet. Yeah, and from this is from the north to the source, like that. Does it make sense to you? Yes. Okay. And okay. Let's talk about the current in a solo. Currently in a solenoid. Yeah, a solenoid is a series of current loops placed along a common axis, and the field outside is very weak compared to the field inside. You can see here is the inside, here inside. This is outside, and like the field outside actually is very weak compared to the field inside. And inside the solenoid, the magnetic field lengths are reasonably evenly spaced. The field inside is nearly uniform. You can see. This is a simple drawing. This is just like the inside. The inside the solenoid, the field lengths are like reasonably evenly spaced. Yeah. And the field inside is nearly uniform. And magnetic field lengths due to current have no start or end. You can see there is no start. Yeah, no end. It's just a circle. Yeah, it's just a circle. It's just a circle. Yeah. And they form complete closed curves. Yeah. If we consider the field length continually inside a magnet, we find that these lengths also form complete closed curves. If we just consider the field length, actually we didn't talk about the inside the magnet, like how the field length look like inside the magnet. If we just look at like look at this consider the field length inside a magnet, we find this length also from complete closed curve. It's just from the north and to the source, and from north to the source, and circle curved. I cannot see it serve is a circle, it is a curve. Close the curves. Okay. And ordinary magnets are often called permanent magnets. To distinguish their unchanging magnetism from that caused by currents that can be switched on and off. Yeah, usually some magnet permanent magnet, which means no matter what happens, these permanent magnets also have the electric field around around it, but that magnetic field caused by current, you can see current sometimes it will disappear if there is no power of there is no motion of charge. Yeah, so the magnetism will disappear. The magnetic field will disappear when it is caused by current. Yeah, so if it can, the magnetism field around it cannot be removed or disappear, we call it permanent magnets. Yeah, that makes sense to you? Okay. And here, let's talk about the magnetic field of a straight current carry wire, firstly. And the iron filings line up in circles around a straight current carrying wire. You can see this is when the current up. Yeah, this is the current up situation. Here, this is a current carrying wire. And there are some small compass. Yeah, the compass needles are tangent into a circle around the wire. You can see if there is a circle. If you, yeah, this compass is just this compass needles are tangent to a circle around the wire, showing that the field is directed counterclockwise around the wire. If because this is north, this is south, which means it's just this direction, this direction, this direction, this direction, yeah, this direction, this direction. Yeah, so it is the field is directed counterclockwise around the wire. Yeah, if the current is down, this is current down, and there are also some small compass around this, and if you connect this, and you will find the compass needle turns to point in the opposite direction. You can see, so this is a north, and this is a electric field direction. This is the electric field. This is the electric field. It is clockwise. Yeah, that makes sense to you. Yeah, this is this is current direction, and the magnetic field direction. The relationship between current direction and the magnetic field direction. Yeah, you can see. Then we can use the right-hand rule of fields help us to remember which direction compasses will point. Yeah, this rule, right-hand rule of fields, is very important. Yeah, so you need to use it very well. Yeah, remember this right-hand rule very deeply. Yeah, just remember this rule. Yeah, you can find this right-hand rule for fields in a tactics box 24.1. It is in the page number 845. Yeah, let's talk about what is right-hand rule of fields. Yeah, point your right thumb. Yeah, this is your right thumb, not left arm, right hand, right hand. Remember that. Even you are a left-handed user, you just use right hand. Don't be paying attention to that. Okay, use your right thumb in I here is current, the direction of the current. Yeah, just a point. Use your right thumb, point to the direction of the current, and wrap your fingers around the wire to indicate a circle. Yeah, just like use here, wrap your finger around the wire to indicate a circle, and your fingers curl in the direction of the magnetic field lines around the wire. Actually, your fingers curl in the direction. You can see it's just the same direction of the magnetic field lines around the wire. Okay, let me show. Can you see my face? Wait me for a moment. Okay, you can see, this is this one. Yeah, this is your right hand. And this, your right thumb is just the like current direction. And this one, your finger, just wrap your finger. And this will be the direction of magnetic field length around the wire. Yeah, we call this is a right hand zonal fields. Okay, let me continue to share my screen. Oh, oh, sorry. I think I just this okay. Okay, let me continue. Oh, sorry. I just share the wrong uh thing. So yeah, this one is what I need to share. Okay, let's continue. So this is like a right hand rule, and just remember that, and we will talk about how to use it. Okay. Okay. Yeah. Magnetism often requires a three-dimensional perspective. Yeah. And to indicate field vectors or currents that are perpendicular to the page, we use this one, this like a X shape, yeah, which means the vectors into page, yeah, because this one is just represent the vectors into page, and this is the current into page. Yeah, we use this symbol to represent the current into page, and this is the vector out of page, and this we use this one to represent current out of page. Okay, just remember this. Yeah, it will help us to analyze the magnetic field around the circuit. Okay. Here is an example of the of the notation with compasses around a current that is directed into the page. You can see this one, and which means the current like into page. Am I right? So, like when you let me stop share. Yeah, which means like for example here, this one is just into the page. For example, your screen is a page, am I right? So which means this one will be the like a direction of the electric field. And also, yeah, you can see. Sorry, let me share screen. Yeah, if you use like a if you use the like a right hand, then you can see this is just the direction of the magnetic field. Yeah, that makes sense to you. Okay, let's talk about this. This some questions to practice the right hand rule. Yeah, a long straight wire extends into and out of the screen, and the current in the wire is what? Yeah, we just use the magnetic the right length, the right hand rules. You can see. Wait me for a moment. Let me share what okay, wait me. Yeah, for this question, yeah, we can use the rule, the right hand rule, and to decide the the current direction. Actually, if we know the current direction, we can use right hand rule to decide the magnetic field direction. And oppositely, if we know the magnetic field direction, we can use the right hand rule to decide the current direction. Yeah, because you can see here, and this is uh, this is the north direction. Yeah, this is like a magnetic field direction. This is a magnetic magnetic field. So it is like a counterclockwise. Yeah, it is counterclockwise. So which means just this one. Am I right? Yeah. And then what's the direction of the current? It should point you like out of the screen. Am I right? So which means the answer should be out of the screen. Does it make sense to you? Yeah. Okay, let's talk about this one. Yeah. And you can see the point P is 5. No, if I can. Yeah, it's 5 centimeter above the wire as you look straight down at it. In which direction is the magnetic field at P? Yeah, which means this one is just uh you know you can also use the right hand rule. Yeah, definitely, absolutely. And then you can see this one you also use, and this is current of direction, current direction. And then this will be the a magnetic field direction, am I right? And the P, you can see it tells us it is 5 centimeter above the wire, and as you look straight down at it, which means this P is just from this direction, am I right? So which means the magnetic field should be what? Down down should go down, goes down. Does it make sense to you? Yeah. So which means it's just the magnetic field is just like this direction. So which means it is the right answer should be D. Does it make sense to you? Okay, let's continue to talk about this one. Yeah, and stretch the magnetic field of a long current carrying wire with the current going into the paper. Yeah, which means the current going into the paper, which means it should be just like this. Draw both magnetic field line and magnetic field vector represent uh, represented representations. Okay, like okay, I think let me share my stop share and share only the screen. That will help you to, yeah, I think this will. Yeah, from the iron flame picture in the atlas, we have seen that the field length from 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 circles around the wire and the magnetic field becomes weaker as the distance from the wire is increased. This figure, yeah, this figure shows how we construct both field length and field vector representations of such field. You can see, firstly, we know the current goes into the paper, so which means this is the current direction. Am I right? And then, yeah, you can see this means current goes into the page, and then you use the right hand rule, point your right thumb in this direction, in this direction, and you can find the direction of the magnetic field. Yeah, you will notice your figures curve clockwise. Yeah, and so the magnetic field lengths are clockwise circles around the wire. Yeah, this is the field, electric field, like a length. And you can see the magnetic field vectors are longer where the field is stronger. Yeah, actually, you can see, and here is the strongest, and this is maybe weaker, 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 and this is this long, and this one here, maybe it is longer than this one, and also here it is longer than this one. Yeah, and the magnetic field vectors are tangent to the field length. Yeah. Yeah, it's tangent to the field length. And the field lengths are closer together where the field is stronger. Yeah, we just talk about that. Yeah, you can like clearly draw this picture by yourself. And yeah, the figure illustrates the key features of the field. The direction of the field vectors and the field length matches what we saw in figure 24.30. Yeah, this one. Oh, sorry. Let me show it to you. Oh, um, yeah, this one. This is like a picture 2430. Yeah, and then you can see. Oh, sorry. Yeah, and yeah, this the direction of field vectors and the field length matches what we saw in that figure, and the field strength drops off with the distance, as we learned in the atlas figure. Yeah, that makes sense to you. Okay, let's continue to assess this result. We do not expect you to draw such a figure, but it's worth looking at the full 3D. Yeah, this figure. Yeah, but it's worth looking at the full 3D picture of the field in this figure. This conveys the idea that the field length exists in every plane along the length of the wire. Actually, you can see if there is a wire and this wire, there is a current through this wire, and there will be an electric field around this wire. Yeah, it's just similar like that. Actually, it's everywhere like that. Does that make sense to you? Okay, let's talk about the magnetic field of a current loop. Yeah, we just talk about the like a single single wire, and let's talk about the current for like the magnetic field of a current loop. Yeah, here we see three views of a current carrying loop. Yeah, here this is a current loop, and this is the direction of the uh, current. And also, yeah, this is a imaginary plane cutting loop. Yeah, if you here there is a loop. If you cut this loop from here or from here, and then you can get this picture. Yeah, and this is the current coming out of the because you can see this is the direction of the current, which means it is go out. Yeah, go out the page, and this is going to the page, current going to plan. Yeah, this is coming out of the plan. The edge view of the half of the loop behind the plan. This is the edge view of the half of the loop behind the plan. That makes sense to you? Yeah, you just yeah, cut this from here, cut, and from here, cut, and then you can get this image, and this means the current coming out of the plan, and this means the current going into plan. That makes sense to you? Okay, and to see what the field due to a current loop looks like, we can imagine bending a straight wire into a loop. Yeah, you can imagine just bending a straight wire into loop. The field lines near the wire will remain similar to what they looked like when the wire was straight, circles going around the wire. Yeah, if you yeah, you can see. And further from the wire, the field lines are no longer circles, but they still curve through the center of the loop, back around the outside, and then return through the center. Yeah, if we reverse the direction of the current in the loop, all the field lines reverse direction as well. Yeah, this is just like the features, all the features for the magnetic field of a current loop. Yeah, you can see. Yeah, And let's talk about more. Yeah, this is just like the images. Yeah, the view of the loop from the left side. This is a view, like a view of loop from left side, and this is a face-on view of the loop. And you can also check this video for the magnetic field of a current loop. Yeah, we will now play the video here, and to save the time. And you can see here, this is like a loop, and it's just like this is just the current direction. It is face to us, and this is just like goes into the page like that, goes into the screen. And use the right hand rule for the fields to find the direction of the field lines. You can see if you use your just like use the right hand rule, you can find the because you know the current direction, am I right? So you can find the magnetic field direction. It's just it's just like this. Yeah, your finger. Does it make sense to you? Yeah, and if you this is the direct current direction, and this is just the yeah, does it make sense to you? Yeah. And near the where the field lines are almost circular, you can see, oh, yeah, it's just almost circular because you can see if you zoom in, it's just a straight line. Yeah, yeah, if you zoom in, sorry. Uh, yeah, if you zoom in, and it's just like for this um, for this part, it's just a straight line. Does it make sense to you? Okay. Yeah, and it's almost a circle. Yeah, and the field emerges from the center of the loop because here there is it's just not like the straight where. Yeah, there is everywhere that will not affect the other place. Yeah, but for a loop, you can see here in the middle, like in the center of the loop, the field merges here from the center. And yeah, so just merges here and returns around the outside of the loop. Yeah, and it will returns. Yeah, outside of the loop. It's just like this. Yeah, and goes out and return, goes out and return, goes out and return. Yeah, doesn't make sense to you. Okay, and okay. After we talk about this like magnetic field and our current loop, let's review some like quick check questions. Yeah, here, the following diagram shows a current loop perpendicular to the page. Yeah, the view is a slice through the loop. The direction of the current in the wire at the top and at the uh, at the top is showing. What is the direction of the magnetic field at a point in the center of the loop? I think that one is easy. This one is easy, and am I right? So you just use yeah here you use the right hand rule to find the direction of the electric the magnetic field, and then you will know the like that makes sense to you the direction this middle point magnetic field direction. Yeah, so just put your right hand, and you can see this one, which means it is what goes uh, go out of the screen. Does make sense to you? You can see here. Yeah. Oh, sorry. Yeah, this is just a go out of the coming out of the plan, and this one is like going into the plan. So yeah, similar with this one. This is just going out of the plan, and then this is going into the plan. So which means you use this, you use your hand, and this will be your bigger curve direction. Does it make sense to you? Yeah, let me share, stop share, and yeah, and you can see this is just the uh this is going to and go out, and so which means So like this is go out. So which means it is should like this, am I right? Yeah, so which means this what's this direction? It will goes to where? Right, am I right? So let me continue to share my screen. Yeah, it should the answer should be the C. That makes sense to you. Yeah, just use the right hand rule to like try to figure this out. And let's talk about this one. Where is the north magnetic pole of this current loop? Yeah, you can see here. It asks us the north magnetic pole of the current loop. We know like the north means it like away, just go away. Am I right? So which means you can see like this one. Um, yeah, which means for this it should be in S, am I right? Because we know like the electric field, magnetic, not electric. Sorry, I always mess those two up. A magnetic field, it will go out from the north and it goes into the south. That makes sense to you. So which means if this it let us this one let us to find the uh where is the north pole, like north magnetic pole? Yeah, just use your like a magnetic, just use right hand rule, and to yeah, you use the right hand rule, and this is just out of like a sorry, this is just out like coming out from the plant, and this is going to. So which means it you're like a magnetic field direction should like this. Am I right? And we know like the magnetic field should from the inside is from north to like south to north, and then out. That makes sense to you. So this means this is north, and so it is to the bottom side. And let me show my face and let you to you can see this one is just the direction of the current. Yeah, this and face to us, and then you just use the like a right hand rule, and you can see this direction is just the magnetic field direction. It will go down. That makes sense to you. And the inside it should be from north, from south to north. Outside should from north to south. Does it make sense to you? Okay, let's continue to share. So the right answer should be B. That makes sense to you. Okay, let's continue to talk about the magnetic field of solenoid. Yeah, we talk about the like a magnetic field of a single straight wheel, and also magnetic field of a loop current. And now let's talk about the magnetic field of a solo no noid. And there are many applications of magnetism for which we would like to generate a uniform magnetic field, a field that has the same magnitude and same direction at every point within some region of space. Yeah, actually, sometimes we want to like generate a uniform magnetic field to use maybe generate like some forces to let some balance something or some other like applications. Yeah, and a solenoid is a long coil of wire with the same current I passing through each loop or turn. You can see this is just a turn. I don't know, have you ever saw a solenoid? Actually, I think it's common in our real world. Sometimes you can find this solenoid in many like electrical equipments. Yeah, and you can see here this is current goes into and this is go out because this is just a circle like that. I think you guys must have saw this before. Yeah, and the field within the solenoid is strong, meaning parallel to the axis, and reasonably uniform, whereas the field outside the solenoid is very weak. Yeah, let me let me show you the this one. You can see here is just the cut. This if you cut this uh, solenoid from this direction, yeah, cut it, and then you can get this one, and you will find the field inside the solenoid is quite uniform. Yeah, it's quite uniform, and the field is much stronger inside the solenoid because every field line out there, out here, yes, out here, and also must squeeze through here. Yeah, and you can see the outside is quite weak. Yeah, like okay, let us talk about some like quick check questions firstly, and then we will talk about more about the solenoid, like solenoid current, like for magnetic field. Okay, what is the direction of the current in the solenoid as viewed from the top? Yeah, actually, you also can use like right hand rule. Yeah, try do that. Yeah, which does the current flow. Yeah, this is just yeah, the current maybe is from this one to this one, or it's from uh, this one to this one. But you use the here is the magnetic field direction. So which one is the right one? Try to use your current your rule. Yeah, you just like just pick up one turn. I'm sorry. Yeah, you just pick up one turn, and this is just the magnetic field direction. Am I right? So which one will be the like a current? It should be goes to this direction. Am I right? Goes to this direction. Does it make sense to you? Yeah. If it, oh, sorry. Yeah, yeah, it will go to this direction because you can see. Let me show my face. You can see this is like the magnetic field direction. Am I right? It is goes up. Yeah, you can see, and which means this one should be your current like direction. Am I right? So which means it should be. So let me share. Yeah, it should be goes from this one goes to this direction, which means it should from this one to this one, because if you goes from this one, it goes to this one, goes to this one, and then you can use it will be the magnetic field should up. That makes sense to you? Yeah, it should be what? Clockwise or counterclockwise? It should be counterclockwise. That makes sense to you? Yeah. Okay, let's continue. This is the magnetic field of a solenoid. Actually, we will talk about this magnetic field of solenoid more, like in next section. Yeah, like let's talk about the calculating the magnetic field due to a current. And you can see the magnetic field strengths are measured in Tesla. Yeah, familiar with this thing, but this is not that car. Yeah, it's actually Tesla is a very famous physician in the history. Yeah, so and we just use Tesla to uh as to be the magnetic field strength unit. Yeah, and one Tesla is quite a large field. Actually, one Tesla is quite a large field. So most of the field strengths you will work with are much less than 1 Tesla. Yeah, you can see here 1 centimeter from a wire with 1 amp current is just only this like a 2 μ Tesla. That makes sense to you. And this is surface of the Earth is only this small like field strength, and this is 1 centimeter from where with blah blah blah. And you can see the world's strongest magnetic is 45, like a Tesla. Yeah. So there are different like field source and location. It has different field strengths, and you can use this like in some calculation. Okay, and the magnetic for the whale, like for the whales, let's try to figure out how to calculate the magnetic. Yeah, the magnitude of the magnetic field around a long straight current carrying wire depends on the distance r from the wire and the current I through the wire. So this is the equation for like a magnetic field due to a long straight current carrying wire. And the equation is only exact for an infinitely long wire, but it's quite accurate if the length is much greater than r. Yeah, if this r is just like a, for example, yeah, this is r. Yeah, sorry. Yeah, this is r. This is also r. Yeah, r. And if the length of the wire is much greater than the r, and this equation can be applied very well. Yeah, and mu zero is the permeability constant. Actually, this one is just a constant. Yeah, it just the value is around this one, and it relates the strength of the magnetic field to the currents that produce it. Yeah, so you just like if you use this value is constant, you just use this value. Okay, and let's yeah, this is suppose that the field has magnitude B0 at a distance R0 from the well where and twice as much as far away the field is half as strong, because you can see we just the B equal what, the magnitude equal mu 0 I 2 pi r. That makes sense to you? Yeah. And then you can see if the twice as far away, which means this one become 2 times, let it become 2 times, it will become mu I. Am I right? Mu 0 I, which means it is half the original one. The field is half as strong. Does it make sense to you? Okay. Yeah, this is you can draw the magnetic field. Yeah, this is the direction, and this is like how the strength of the field change as the distance from the wire change. Yeah, that makes sense to you? Okay, let's check some like quick questions. Yeah, compared to the magnetic field at point A, the magnetic field at point B is, yeah, we just put the B equal what, mu 0, mu 0 I 2 pi r. Am I right? Yeah, this is just a constant. And for the A and B, the current is the same. Am I right? So which means one is 2 centimeter and the other is 4 centimeter, which means half. Yeah, the magnetic field at point B is half as strong. But you can see if you use the right hand rule, which means the direction here should be go out and here is go into. Yeah, so it is opposite direction. Does it make sense to you? So which means is the right answer should be half as strong opposite direction. Yeah, does it make sense to you? Okay, let's talk about the magnetic field from more than one source. Yeah, the total magnetic field at any point is the vector sum of the individual fields at that point. This is the principle of superposition. You can see this is for the magnetic field. Also for the electric field, for the electric potential, for the electric like it also like have this rule. Yeah, the total magnetic field at any point is a vector sum of the individual fields at that point. This is, yeah, for example here, yeah, you can see there are two different magnetic field. Yeah, those two field, the total is just like a field due to the current and the magnetic. Yeah, this is due to the current because it's come from this current, and this is from this magnet. Yeah, and the total will like the vector sum. Does it make sense to you? Okay, let's see an example. The magnetic field at point P is 0. Yeah, what is the magnitude and the direction of the current in the lower well? Yeah, actually, sorry. Yeah, for this like a problem, you just use the equation. We talk about B equal mu 0 I divided 2 pi r, and also use the rule like a right hand rule to decide the direction, and for the magnitude, just use this equation. Yeah, for this question, like for the magnetic, you can see here P point P, and the magnetic field is 0, and the current in the lower well must cancel the field created by the current in the upper well. Does make sense to you? So like the current in the lower well like must go to left. Yeah, because the direction you want it here is be 0. It should be opposite. The direction should be opposite. Yeah, the direction should be opposite, and the magnetic field strength is inversely proportional the distance from the wire. So the field at P due to the lower wire is 2 times that due to the upper wire. If they have the same current, the current must therefore be 5A in order to produce an equal. Yeah, you can use this equation. Yeah, because you can see the R, it is like one is 4 and 4, the other is 8. So which means this one should be half this one, and then the B, the magnitude is same, but the direction is opposite. Does it make sense to you? Yeah, so which means this should be 5A, and the direction should go to left. Yeah, and then it will produce an equal and opposite magnetic field at P. Does it make sense to you? Yeah, you can review it again. Okay, let's continue. Let's talk about this one. And too long, talk about this example, like finding the magnetic field of two parallel wells. Yeah, it's similar to the one we just talked about, but yeah, let's talk about this one. Two long straight wells lie parallel to each other as shown in the figure. They each carry a current of 5.0 amp, but in opposite direction. Yeah, which means it is 5.8. Oh, sorry, it is 5A. 5A, yeah. But in the like opposite direction, what is the magnetic field at point P? Yeah, I think it's very similar with that one. Yeah, the magnetic field at the point P is the vector sum of the field at P due to each of the wires. Because the magnetic field due to a wire forms circles around the wire, the field due to wire 1 and 2 point either outward all into the plane of the page. Yeah, we'll talk about this just now. And the vectors are much easier to visualize when they are in the plane of the page. So we redraw the two wires as seen from their ends. So their magnetic field lands in this plane. This is wire 1. This is wire 2. One is just go into, and this one is just go out. And then this is the P, and this is 8 centimeter. This is another 8 centimeter. Yeah, the wires as redrawn this way are shown in the figure. We have also added a coordinate system. Yeah, there is a coordinate system. In this view, the right-hand rule for fields tell us that the magnetic field at P from the wire 1, yeah, points to the right. Yeah, if you use like if you use like the right hand rule, because it goes into the page, yeah. So then you can see the direction through this to the right, and the that from where to the left, yeah, from where to the left, and because where 2 is twice as far from P as where 1, we've drawn its field B2 half as long as field B1 from where, because the current is the same. Yeah. So because the distance is just twice, so which means like the field is the electric field is twice. Oh, not electric field, magnetic field is twice. From the figure, we can see that the total field, yeah, this is the total field. And the vector sum of the two field B1, B2, yeah, points to the right because this one is bigger. I'm right. Yeah, to find the magnetic field B, we need the magnitudes of B1 and B2. So we use this equation. Yeah, we use equation 24.1 to find out these magnitudes from the figure. R from where 1 is 8 centimeter, and where R from where 2 is 16 centimeter. Yeah, then we have this equation and put every value here, and we can got the B1 and B2, and then we use the B1 minus B2, and then you can got yeah, because the direction is opposite. Yeah, so you can got the final like field, electric field, magnetic field. Yeah, in terms of original view of the problem in the first figure, we can rewrite yeah, this one, this like magnetic field equal the magnitude is this one. This is like into the page is the direction. Okay. Does it make sense to you? So, like, because the final result is positive, which tells us that the total field points to the right in the same direction as the field due to wire 1. This makes sense because P is closer to wire 1 than to wire 2. Yeah, table 44.1 gives the field 10 center, sorry, 10 centimeter from a wire, carrying 1A as 2 mu Tesla. And the field in this problem should be about the same size. Yeah, the distances are about the same. The currents are larger, but there are two opposite fields. So the magnitude of our answer makes sense. Does it make sense to you? Yeah. Okay. Let's talk about the current loops. Yeah, we talk about the like the magnetic field, how to calculate magnetic field for the wire. Sorry. Yeah, for wires. For now, let's talk about like for the current loops, how to calculate the magnetic field. Yeah, the magnetic field due to a current loop is more complex than that of a straight wire. Yeah, we talk about it. The field as the current depends on actually because the loop, yeah, we know like the field at the center depends on if a straight for a straight wire it depends on the I and the like distance. Actually, for the current loops, it's also like a similar. Yeah, because the loop can be thought as a wire bent into a circle. The expression for the strength of the field at the center of the loop is similar to that of a wire. Yeah, we use this one, this equation. Yeah, this is just the constant, and this is the current. This is R is just the this to the center, the distance between the wire loop to the center. Yeah, center of the loop. Yeah. Yeah, we use this equation to calculate magnetic field at the center of a current loop of radius R. Okay. Yeah, if N loops of a wire carrying the same current I are all tightly wound into a single flat coil, then the magnitude of the field at the center is just N times bigger. Since we are imposing N individual current loops, so if there is N loops, So just a multiple n here, yeah. Because it just like n, like a yeah, we just since we are imposing individual current loops, that makes sense to you, yeah. Okay. So this is just this is one for one loop, current loop, and this for the n current loops, and how to calculate the magnetic field. Okay, let's talk about this example, like a question, canceling the Earth's magnetic field. Yeah, green turtles are thought to navigate by using the deep angle of the Earth's magnetic field. To test this hypothesis, green turtle hatchlings were placed in a 72 centimeter diameter tank with a 16 turn coil of wire wrapped around the outside. A current in the coil created a magnetic field at the center of the tank that exactly canceled the vertical component of the Earth. 50. Yeah, we have already talked about. We can find this in the table we have already talked about. Yeah. 50 mil Tesla field, and at the location of the test, the Earth field was directed 60 degree below the horizontal. What was the current in the coil? Actually, yeah, like this figure shows the Earth the field passing downwards through the coil. Yeah, this is a coil, and this is just go out the like plane. This is going to the plane, and this is this is the field of the coil using the like right hand like right hand rule. Yeah, that makes sense to you. Yeah, so which means yeah. This is just the vertical component of Earth's field. Yeah, this is the Earth's field. Uh, that makes okay. Yeah. And to cancel the like vertical component of this field, the current in the coil must generate an upward field of equal magnitude. We can use the right-hand rule to find that the current must circulate around the coil as shown. Yeah, this one. Viewed from above, the current will be counter clockwise. Yeah, if you look view from above, and it will counter clockwise. And then you can use the vertical component of the Earth field is this one. Yeah, this is uh Earth field, like a Earth field magnetic, and this is just the angle you can see, because yeah, you can see it has I have already given you this is the Earth field, and then there is a 16 because the Earth field was directly 16 below the horizontal. Yeah, so which means the this component should be like this one. This one should be this sin, yeah, sin 16 degree, and then this is like a y. I think this is yeah y component for the electric earth field. Yeah, that makes sense to you. Okay, and the field of the coin given by equation 24.3 is just like B equal mu 0 I divided to R. Yeah, must have the same magnitude at the center. If because there is 16, so you need to add n here. Yeah, so which means yeah, the 2R in the equation is just the diameter of the coil. It is 72 centimeter or 0.72 meter. Yeah, so you just put the constant here, and put the n is 16, and I yeah, you need to calculate it, and then this is what we know. So, and this is yeah, this magnitude this magnitude yeah should equal this magnitude, yeah, and then we can calculate the current using this equation, and it is around 0.41, and as noted, this current is counterclockwise as viewed from the above. Yeah, we talked about just now. And yeah, and let's assess this result. Equation 24.3. Yeah, this one, B equal mu Ni divided to R. Yeah, that shows that the field in the center of the coil is proportional to the number of turns in the coil, proportional to the current, and inversely proportional to the radius of the coil. Table 24.1 gives 0.01 Tesla for the field in the center of a 100 turn coil that is 1 centimeter in the diameter and carries a current of 1 amp. The coil in this problem is nearly 100 times larger, carries about half as much current, and has about half as many turns. We therefore predict a field that is less than the table 24.1 value by the factor of a few hundreds, which it is. A rough estimate of the answer agree with our result, so it seems reasonable. Yeah, does it make sense to you? Okay. Any question, just let me know. Okay. And let's talk about this example problem. And a physical, let's read it. A physics instructor is creating a demonstration that shows the direction of a field at a center of a current loop. He takes a cardboard from 25 centimeter in the diameter and wraps 20 turns of wire around it in a tight loop. He wants the field at the loop center to be at least 10 times as large as the magnetic field of the Earth, so that a compass will pivot conventionally to point in the direction of the field from the loop. How much current is needed to provide this field? Yeah, actually, I think we just use the equation like B equal mu 0 Ni divided R2. Yeah, and because here, this question asks how much current, and we know like the N is 20, 10, and this mu 0 is, we know it is a constant, and R is here is 2R is 25. Am I right? And we know like he wants the field at the loop center to be at least 10 times as large as the magnetic field of the Earth. We know the magnetic field is 5 multiple, yeah, like Tesla. So which means it should be 10 times like 5 multiple and -5, power -5, and then you can use the equation to calculate the current. Yeah, does it make sense to you? Yeah, just just try to calculate it by yourself. Okay, let's talk about more about solenoids. Yeah, the field inside a solenoid is fairly uniform. We talked about it just now. The field outside is quite small. The greater the solenoid is the length in comparison to its diameter, the better these statements hold. Yeah, solenoids can be built quite large. The cylinder that surrounds a page is surround surrounds a patient undergoing magnetic resonance. Imagine like an MR contains a large solenoid. Yeah, does it make sense to you? Yeah, and you can see the equation 24.4, this one, gives the magnitude like B equal mu 0 And oh yeah, uh, huh? Sorry, we will talk about this equation later. Yeah, I haven't talked about it. Yeah, so just yeah, and yeah, we will like I will give you the equation for like calculating the magnitude of uniform field inside the solenoid. Yeah, the direction of the field is given by the right-hand rule for the fields. Yeah, this is some like features for like the electric magnetic field for the solenoids. Yeah, and you can see the greater the ratio of n turns of wire to the length L of the solenoid. Yeah, and the stronger the field inside will be, which means if this one greater and the field will be stronger. Yeah, the strength of the field will also be proportional to the current. And the field does not depend on the radius of the solenoid. Yeah, just the one single current loop depends on the like radius no yeah, but the field for the solenoid is not dependent on the radius of the solenoid. Yeah, the equation should we use this equation to calculate the magnetic field inside a solenoid of length L with n turns. Yeah, just remember. Yeah, okay. Let's check some like questions. Yeah, the current in the solenoid noid. Yeah, you can see it asks us the current. Yeah, we just need to use the like right hand rule. Yeah, you can see it has already given us the magnetic field direction, and then you can see just get one like and you can see if you let the which means the direction should go this direction. Am I right? So it should be enters on the right, leaves on the left. It should be B. That makes sense to you. Yeah, right hand rule. You just choose one, like uh, choose one circle and use the right hand rule. That makes sense to you. Okay, let's check this one. Yeah, solenoid 2 has twice the diameter, twice the length, and twice as many turns as solenoid 1. How does the field B2 at the center of solenoid 2 compare to B1 at the center of solenoid 1? Actually, this one is not difficult. You just put the equation here, B equal what? B equal mu n I divide L. Am I right? Yeah, just this direct, just no this one. Yeah, just this one. Yeah, you use this equation, and then oh sorry, and then you will see like the B. This is B1. Yeah, and like it is just twice the diameter. Yeah, actually it's not related to the diameter, twice the length. So which means the magnetic field will half. That makes sense to you. Yeah, because the length, if you twice the length, it will half. And twice as many turns as yeah, you just turns twice. So which means it will be equal. And the okay, if the current is the same, so which means I think it will be the same. Does it make sense to you? Okay. So which means yeah, it should be same using this equation. Yeah, I think this question just forgot to tell you the yeah, it I already tell you the current is the same. Yeah, you can see here is I, here is I. That makes sense to you? Okay, yes. So the magnetic field is same. Okay, let's talk about this like generating an MIR magnetic field like example. This is about biology example. A typical MIR solenoid has a length of about 1 meter and a diameter of about 1 meter. A typical field inside such solenoid is about 1 Tesla. Oh, it's huge, am I right? How many turns of wire must have the solenoid have to produce this field if the largest current the wire can carry is 100. And yeah, this we can use it, before we talk about you need to, yeah, an equation should pop up in your mind. Yeah, so you need to use B equal what, mu 0 Ni divided L. I'm right? Yeah, this solenoid is not very long compared to its diameter. So using equation 24.4, yeah, this equation will give only an approximate result. Yeah, this is acceptable since we have only rough estimates of the field B and the length L. Yeah, you can see here is just around. Okay, and equation 24.4. Yeah, just let me write this equation again. Let you remember B equal what, mu 0 Ni divided L. Yeah, gives a magnetic field of B of a solenoid in terms of the current I, the number of turns N, and the length L. Here, however, we want to find the number of turns in terms of other variables, we need a B equal this one, I equal this one, and L equal this one. Okay. And we can solve equation 24.4 for N to get, yeah, get this one. Yeah, just B equal mu Ni divided L. So which means the N equal BL divided mu 0 I. That makes sense to you? Yeah. And then you put every value here, and then you can get N equal 8,000 turns. Yeah, it is a significant value. Am I right? Yeah, the number of turns required is quite large, but the field is quite large, so that makes sense. Okay. Yeah, let's talk about this example problem. And yeah, an investigator needs a uniform 3 empty field, like which she intends to produce with a solenoid. She takes a long, like a 10 centimeter diameter tub and a wrapped wire along the length of it, wrapping 1,200 turns of wire along a 75 centimeter length of the tub. How much current must she pass through the wire to produce the desired field? Yeah, actually, I think for this question, you just need to figure out what is the N, what is the I, what is, yeah, oh, sorry, they just let you get the I. So what is N, what is B, what is, yeah, you just write the equation here, mu 0, you have already know that it's a constant, and Ni divided L, and you need to, what is N, what is B, what is L. Yeah, so for N, it is 1,022, am I right? And 200. Yeah, and for B, it's this one, needs a uniform 30 Tesla field. Yeah, and for the L, yeah, actually there are like this should be the L, 75 centimeter. Yeah, that makes sense to you. And then you use this equation to calculate the current. Yeah, I will not calculate it. You can calculate it by yourself. Okay, let's talk about, yeah, do a summarize. And we like talk about like calculating fields from currents. And you can see there are some different situations. Yeah, an electric current produces a magnetic field. The geometry of the field depends on the geometry of the conductor. You can see here. This is for a wire. Yeah, we use current in a long straight wire creates a magnetic field that encircles the wire. Yeah, we can use this equation to calculate the magnetic field from a straight wire. Yeah, long straight wire. Yeah, and this is the direction given by the right-hand rule for the fields. Yeah, we can use the right-hand rule to decide the magnetic field direction. And this is the permeability constant. Yeah, we just use it. Yeah, And then this is the for a single, yeah, electric current produces a magnetic field. Yeah, this is for a single circle loop. Yeah, and and this this is a coin is a standard loop with a length small compared to the radius. We treat this as a loop with multiple turns. Yeah, this is it's just for the yeah for different for the like a circle loop, yeah, but you can put a many circle loop, and for the current in a coin or loop field length emerge from the center of the loop and wrap around it in a direction given by the right hand for the field. Yeah, you can see this is just the number of turns, and you will have the question, what's the difference with this one and the solo node. Actually, for this one, you can see this is just a one circle, one circle, one circle, put them close together. Yeah, but the solo node is just this one, it's not like it's connected, it is a whole thing, it's connected. This is just like a coin is a stack of loops. Yeah, that makes sense to you. Yeah, so you can use this equation. And then for a solo node, yeah, you can use this equation. Yeah, because this is just a whole thing. And for the direction, you all those three situations, you can use the right hand rule, yeah, to decide the magnetic field direction. Yeah, that makes sense to you. Okay, and let's talk about the next example problem. What is the direction and the magnitude of the magnetic field at point P at the current of the this loop? Actually, you need to actually this current direction is from here to here to here and then go out to here. Yeah, this is for the direction. You just use the right hand rule, and you can see if you use the right hand rule, and you can see the magnetic field direction should goes into the plan. That makes sense to you. And then you can use this equation, B equal mu 0, because it is only one circle. Yeah, so mu 1 like I divide 2r, like then to calculate the magnitude for the magnetic field. Yeah, does it make sense to you? Okay. Yeah, this is what we talk about in this class. Yeah, we talk about the magnetism. What is magnetism? And what is the magnetic field? And how to calculate the magnetic field? Yeah, we know like the current can like generate magnetic field. Yeah, and but how to calculate it? Yeah, we also talk about that. Okay, this is what we talk about in this class, and we will talk about more things about the magnetic field in next class. Okay. Yeah. See you. Bye.